Okay, remember, limits mean that we're getting infinitely close to an x value, and when we get really, really close to that x value, we're wondering what is the y value that our function is approaching or getting really close to. Well, if we have a function that's continuous, meaning no holes, no asymptotes, no breaks, no gaps, really, we don't pick up our pencil at all when we draw it, then shouldn't we be getting close to the y value that our function actually is? So, in other words, for a function that's continuous at this c value that we're curious about, the actual value of the function will be what the limit is as x approaches c. This is called direct substitution. We're going to learn a ton of different methods to evaluate limits, and a lot of our methods are going to focus on being able to rewrite our function so that we can use direct substitution. Direct substitution is the easiest way to evaluate a function. So this is what we're saying. We're basically saying the limit as x approaches c of our function is the same thing as just plugging c into f, as long as our function is continuous. So if we don't have a continuous function, this doesn't work. So what this means is, let's look at some examples. First example, if I'm taking the limit of some function f of x equals 5 as x approaches 2, well, if you think about what does it mean for this function, if my function is just f of x equals 5, well, doesn't that mean that no matter what my x value is, my y value is 5? So I'm going to get this straight horizontal line. I didn't do a very good job of hitting my points there. So when x approaches 2, aren't I just going to still be at a y value of 5? Okay, so if I have a constant function, my limit, no matter what I plug in, is just going to be that constant function. And I wrote 2 and I meant to write 5, sorry. It's just going to be that constant function. If I look at the next one, the limit, if my function is 3x as x approaches 4, well, I know that this is 3x is a linear function, so I know that's continuous. So I know since it's continuous that I should be approaching the actual value of 3 times 4. So I directly substitute 4 in, and I get a limit of 12. If I were to sketch out or look at a graph of that, I would see that my y values really are getting close to that 12. Limit as x, the limit as x approaches -2 for my function x cubed. Again, I have some knowledge about an x cubed function, and I know that the x cubed function is continuous. Since it's continuous, according to this here, all I have to do is take that value that I'm interested in, that -2, and plug it in, and that will be my limit. So plugging in a -2 cubed is -8. So the limit as x approaches -2 for the function x cubed is -8. Number 4, I have this quadratic equation, -x squared plus 7. Again, I know quadratic equations are continuous. Since it's continuous, I'm going to go ahead and use direct substitution. The limit of this function as x approaches -3 is going to be -3 squared plus 7. Well, that gives me -3 squared is 9, so I have -9 plus 7, and I get a limit of -2. On number 5, I have the function 2x over the square root of x minus 3. I know this is not continuous. The reason I know it's not continuous is because I know that radical functions have domain restrictions. In fact, I'm not going to be, well, maybe not continuous as a incorrect way of stating this. I know this isn't going to be defined for an entire domain. I know that my domain for this is going to have to be x values greater than 3, because anything less than 3 is going to give me a negative number under here. But once I start at 3, I also know that this will be a continuous function. And so since 4 is within my domain, I know my function is continuous at that value. So since it's continuous at 4, I'm going to go ahead and use direct substitution and plug 4 in, giving me 2 times 4 over the square root of 4 minus 3. Well, that gives me 8 over the square root of 1. I know the square root of 1 is just 1, and 8 over 1 is just 8. So if you can determine if a function is continuous at the value that you're looking for the limit at, all you have to do is use direct substitution. Once again, that's going to be our easiest way to evaluate the limit. And I believe that was the last example. Yep, that's all I have on there.